Hello, everyone who joined us in this last session. And as you remember, yesterday we talked about natural Banach function algebras. And I told you if we have a Banach function algebra, the last thing I told you is A is a Banach function algebra such that it is self-adjoint. And if for each f with z of f is empty, we have f is invertible, 1 over f is in A, then we can say that A is natural. In other words, m of A is x. And for example, for C of x, Cn of I, and lip of x, all of them, of course, for C of x, we prove separately, but anyway, from this, we can obtain this. All of these algebras are natural. But you know that this algebra is also uniform algebra and so a Banach function algebra, but it's not self-adjoint, so it doesn't work for this algebra. But anyway, as another example, we can say that AD is also natural. It means that each character in M of A is the evaluation homomorphism. As I told you before, AD is generated by the constant function 1 and z function. This is inclusion map. I mean that z of lambda is lambda. And so from the previous proposition we had yesterday, M of AD is homomorphic to spectrum of Z. It means that Z can determine each character in M of AD. So let's see in M of AD this algebra and put P of Z is, for example, lambda. Then absolute value of lambda is P of Z. It has most norm of phi, norm of Z. We know that this is 1 and this is of course 1, so we have 1 here, and lambda is in T, sorry, in D. And then P of Z is exactly delta lambda of Z. It means that phi is evaluation homomorphism, because if, for example, from that proposition, we can say that, oh, for example, even we have a polynomial like this, phi of Z should be sigma phi of phi is also linear and preserve multiplication. So finally, we have phi n lambda n. And each f is a limit of polynomials, and then phi is continuous. So for each f, and then f, because it's the limit of polynomial, for each f, we can say that phi of f is also delta lambda at phi. This is, of course, is lambda delta lambda at p. And f is limit of, sorry. limit of polynomials. So we have for f also. Each element in maximal ideal space of this algebra is a form of evaluation homomorphism. So AD is natural. It's but the here is because phi is continuous. And f is the limit of polynomials. I didn't write some details, but I just say in orally anyway. Okay. So let's make a connection between Banach function algebras and commutative Banach algebras, we just studied before. The first one, each Banach function algebra on X is a commutative Banach algebra. Of course, it's a commutative. Sorry, it's the same. It's commutative Banach algebra is trivial because we have pointwise operation, and it's Banach, of course. I forgot to write semi-simple. Semi-simple because they are radical of A. We know that the intersection of kernel of P, being maximal ideal of A, but the evaluation homomorphism are also in M of A, and maybe we have another element here. Anyway, so this is subset of kernel of delta X when X in X. Anyway, when F is here, it means that for each X is, f of X is 0. Finally, this is just the function 0. So it's semi-simple. The second part, for each commutative Banach algebra, A hat is a natural Banach function algebra on M of A. You know, of course, it's separate the point, so it's function algebra, and just we need to say this is really Banach and with a norm, and of course it's natural. But we know that according to Gelfand representation theorem, we can say that this quotient algebra is isomorphic to A hat. That's why we define let's write it. Okay, since A over radical of A is isomorphic to A hat, we define norm of A hat to be quotient norm here. Radical is a closed subalgebra ideal of A. So this is a Banach algebra with this norm. But if it's semi-simple, this norm is exactly the norm of A. The norm of A hat comes from the norm of A. But in general, we have to consider quotient norm. And A hat, we show that A hat is natural. So let's find M of A hat, and we have to show that it's like a delta of phi when phi in M of A. It's clear what we should define. Define phi0 from A to C by phi0 of A is a phi of A hat then see exactly the deltas C of 0 because A hat is a subalgebra of C of M of A, and we find element here such that V is the evaluation homomorphism at P0. And the last part, if A is a commutative Banach algebra, just say commutative for emphasize because before I suppose that all algebras are here are commutative, but I just say for emphasize, just have a look and you found all conditions. Anyway, if A is a commutative Banach algebra such that norm of A2 is equal to norm of A squared for each A, then because the Gelfand transform is semisimple, and of course the Gelfand transform is an isometry, we can consider here subnorm and say, and this is, we can say that A hat is a uniform algebra, and of course natural, like before. Natural uniform algebra. The last theorem I told you concerning Gelfand transform, it was this. When we have this equation for each A, Gelfand transform is an isometry, so we can consider uniform algebra, supranorm of I hat here, of course. Natural uniform algebra and M of A. So it's clear from the previous theorem before. Okay. Okay, I want to say, well, we have an isometry, for example, hat from A to A hat, Gelfand transform is an isometry, but this is a Banach algebra, so it will be also uh, closed as a subalgebra of C of M of A. That's why it's uniformly closed, because it's here we have isometry and A is closed, and finally A hat will be closed with supremum no. Now I start with some special concept just in the theory of functional algebras, like boundary. Let's put it first, just not to forget it. A subset E of X is called a boundary for A for a Banach, no, functional algebra. It's not necessary to have one. Functional algebra on X if each f attains its maximal modulus at some point of E. In other words, if for each f in A, there exists x in E such that absolute value of f of x is equal to supremum norm of f. So when we have two functions in A which are the same on each boundary, they will definitely the same on the whole x, because supremum for each f, supremum norm of f is equal to supremum norm of f restriction to E. And so because of this, when two functions are equal to boundary, then they should be equal on the whole x. Okay, I want to say another theorem, but we need some things from functional analysis, extreme point. I don't know if you maybe remember. If K is a convex subset of X, for example, a norm space, or even vector space, also okay. Then A is an extreme point of K. If A is not an interior point of any line segment which is contained in K. In other words, if, for example, x1, x2 in K and T between 0 and 1, and A is T x1, x2, then from this equation, we obtain that A is equal to x1 is equal to x2. So it's not in interior any line segment which is completely in K. And you know that it's not necessary for it to check it for each T. It's enough to consider T is 1/2. So if x1, x2 in K, and A is the average of x1 and x2, then x1 is x2, xa. I mean that this equation implies that the points are the same, and it means that A is extreme point. For example, extreme point of the unit ball, the closed unit ball of C is the unit circle. Of course, it's true for each Hilbert space. I mean that the extreme point of closed unit ball is the unit sphere. Of course, we use it several times. And the other thing I want to tell you, it's the dual space of ASR with weakest star topology, which is a locally convex space. Actually, dual space of ASR with weakest star topology is just A. What does it mean? It means that if lambda in this dual space, then there exists A in A. For example, here we have F, and A in A such that lambda is lambda A. And let's write all of them here. Lambda phi is lambda A of phi, which means that phi of A for each p in A star. This is another thing we needed. And the final thing is M of X, the set of all regular complex valued Borel measures. And you know that this is isometrically isomorphic to the dual space of C of X star when X is compact. Actually, this is the Riesz representation theory. Sorry, theorem. And the relation is this: if mu here, we can define f mu like this, such that f mu for each f is just an integral of f d mu and x for each f in C of x. And the norm of mu here is the total variation of mu. And this is isometrically isomorphism. And isomorphism. Okay, now I want to say this theorem, which is very important. If A is a function algebra on X, then each extreme point of the closed unit ball of the dual space of A with respect to subnorm is of the form of alpha delta X when alpha in T and X in is subset and X in X. So it means that the dual space of the closed unit ball of A with respect to subnorm. So each extreme point is of the form of evaluation homomorphism, of course, with coefficients in unit circle. For proof, let's S this set exactly alpha delta X, alpha in T, X in X. For each X in X and alpha in T, in other words, for each alpha X in S, norm of alpha delta X, I mean the operator norm. This is norm of this element is 1 because it's the supremum of absolute value of alpha f of x finally. Supremum norm of f is at most 1. It has most 1 when we put f1 constant function 1 here. It's exactly 1, so this is 1. And so alpha delta x belongs to the closed unit ball of A star. It means that S is a subset of it. Actually, it is elements in S. So it shows that S is a subset of B of A star. Convex hull of S is also a subset of convex hull of this, but it is convex. So it is itself. And of course, the closure of the closed convex hull, or the closure here, is a subset of B of A star, but we know that it is weakest star closed because it is weakest star compact. And then we have it. If we show that, we have equation here. If we show that ball of A star is the closed convex hull of S, then the result is obtained by, of course, by the aid of Banach theorem and, of course, Millman theorem. And show that then the result follows from Banach theorem and also Millman theorem. You can find both theorems in functional analysis, Rudin, Conway. It doesn't matter which one. Because actually Millman theorem says that if S is a is a compact subset of a locally convex space, here, for example, A star with weak star topology, and closed convex hull of S is also compact. We have it before. We have it here. If we prove this, thanks to Banach theorem, we have, of course, this condition. And finally, it says that extreme point of this guy, which is here exactly B of A star, is a subset of S. That's why the theorem follows from these two theorems. We assume that it's not true. If it's not true, what happened? So for a contradiction, suppose that phi is in ball of A star, but not in S. So we have phi, and of course, I'm sorry, here, closed convex hull of S. Because I want to show this. So we have two sets, phi and also closed convex hull of S. Both are convex because it's closure of convex, and this is convex, compact because this is, anyway, this is subset of V of A star, and this is compact, it's closed, it's compact, and they are disjoint. And I mean that the intersection is empty, convex, compact, and the same, and non-empty. And I want to use a separation theorem in functional analysis. You've seen in functional analysis, it said that there exists lambda in the dual space of A star with weak star topology and gamma 1, gamma 2 in R such that you can find this separation theorem again in functional analysis. Such that real of lambda psi is less than gamma 1, gamma 2, real of lambda phi for each psi in closed convex hull of S. But lambda in the dual space of A star, and I told you the form of elements in the dual space is from, it's exactly A, and so there exists F in A such that lambda is lambda F. So let's rewrite it with lambda F. It means that real of sorry, psi of f, it's less than gamma 1, gamma 2, and again real of phi of psi, phi of f for each psi in closed convex hull of S. S is a subset of this set, so we applied this relation for elements in S, which are alpha, delta, x. Is the form of this. So we can say that real of alpha delta x at f, it means that alpha f of x and so I can write it and I can say that even absolute value of f of x is less than gamma 1. Why? If f of x is 0, it's clear. It's real of f of x is 0 and we have it. Okay. Otherwise, we can consider alpha as a f of x bar over the absolute value of f of x, which is not 0. And so this is an element in unit circle, so there is no any problem. Anyway, we can write absolute value of f of x, real of phi of f. And we know that this is at most absolute value of phi of f, and this is at most norm of f, superior norm of f. We know that this is 1. But we know that, so it's valid for each x. So we can say that supremum norm of f is at most gamma 1 because we take limits. I have to put equation even. But anyway, gamma 1 is always less than gamma 2. And finally, I can get it here, supremum norm of f. But this is impossible because this one is strict inequality. And they are the same. This contradiction shows that the set closed convex hull is exactly P of A star. And the x such that delta x is an extreme point is called the set of Choquet boundary for each function algebra. And Choquet boundary is really important concept in theory of functional algebras, and you will see how it can help in characterizing some operators, which of course, especially isometries. If A is a functional algebra on X, the Choquet boundary for A, which is denoted by, usually by this notation, is defined is the set of x in X such that delta x is an extreme point of the closed unit ball of A star. It doesn't matter if I put coefficient just 1 or I say that it's for some alpha. This is alpha delta x is an extreme point, or I say that for each alpha, alpha delta x is an extreme point, because when we have an extreme point, all coefficients by element by scalars in C will be again extreme point. That's why I put 1. Of course, this is well defined, which is well defined. Choquet boundary is not empty because, it's because of Klein-Millman theorem. When we have in local space, we have a convex and compact subset, then the extreme point is non-empty. And even as you observe, it's actually the closed convex hull of the set of extreme points. And it's not even, I mean that not only is the extreme point is not empty, but also we can recover ball of A star with these extreme points. So anyway, this is extreme, this is non-empty by the Klein-Millman theorem. Okay. And maybe some book like Leibowitz defines Choquet boundary as a set of, as the extreme point of this set instead of ball of A star. And we can say that extreme point of T of A is delta X, X in Choquet boundary of A, where T of A is the set of phi in A star, such that norm of phi is 1, is the phi of 1. This is the very important set in the theory of CS algebras. It is a state space of A. Maybe, as I told you, maybe M of A, for example, in Mn is empty, but when of course n is greater than 1, yes, it's empty, but state space not. Anyway, it's very important set in theory of CS algebras. Anyway, if, for example, it says that instead of considering ball of A star, we could just consider T of A and define Choquet boundary as a set, as points such that there are extreme points of T of A. And it's very easy to prove because if X in Choquet boundary of A, then delta X in, of course, in delta X is an extreme point of ball of A star, and so extreme point of T of A. Because T of A is a subset of T of A is a subset of P of A star. For the converse, and so we have, I mean that we have this inclusion. For the converse, let's find extreme point of T of A, and we show X, and this is the form of delta X in Choquet boundary. Okay. Suppose that C in extreme, because we don't know the form of extreme point. We show that this extreme point is also extreme point of P of A star, and definitely should be this form. For this paper, let's, for example, P1, P2 in ball of A star, and instead of convex combination, I just consider T is 1 over 2, and for example, P1 plus 2 over 2 is P. From this relation, we can obtain that P1 and P2 will be also in P of A. Because of that relation, we have P of 1 is P1 of 1 plus P2 of 1 over 2. We know that this is 1 because this is in T of A. And of course, for example, for normal phi, we can say that this is, of course, at most normal phi, phi1, normal phi2, and over 2. But they're at most 1, this one at most 1, so it is at most 1. Anyway, so I can put equation. And of course, their elements, because norm of each pi is at most 1, their elements in D, in unit ball of C, and 1 is an extreme point of unit ball in C. So 1 is P of 1, P2 of 1, and similarly, 1 is norm of P1, norm of P2. And then P1 and P2, both of them are in T of A. And phi is an extreme point of T of A, so phi should be equal to phi1 and phi2. Then, because phi is an extreme point of T of A, phi is equal to phi1 is equal to phi2. Anyway, this equation implies that phi is equal to phi1 is equal to phi2. It means that phi is an extreme point of ball of A star. Then according to the definition of Choquet boundary, then there exists in Choquet boundary, of course this is unique, such that phi is the form of delta x. Now I want to show that I define a boundary as a subset of X. Each F attains its maximal module at some points of E. I want to show that Choquet boundary is actually a boundary, and it's really meaningful to say boundary for it. Choquet boundary of A is the boundary for function algebra A on X. Maybe it is better to say it first. Anyway, it means that each F attains its maximal modules at some point of Choquet boundary. If F is 0, then it's clear, because Choquet boundary, of course, is non-empty, and each point in Choquet boundary works for you. Then it's trivial, or it holds. So assume that f is not 0. We assume with that lossless generality that supremum norm of f is 1, because otherwise we can consider g f over norm of f, which we know that this is not 0, and f attains its maximal modules at, for example, point x. G is also, that point is also for x, and the converse, and that so doesn't matter if we can consider norm of f is 1. Otherwise, we can consider work with this function, and each point here works also for f. And supremum norm of f is 1. So we can assume. I just say that because I wanted to tell you because of this one. We can assume without loss of generality, supremum norm of f is 1. Define or put this set like this. In ball of A star such that phi of f is 1. Since supremum norm of f is 1 and x is compact, there exists x in x such that absolute value of f of x is supremum norm of f, which is 1. And so delta x over f of x is an element here because p at x is at f is 1, and of course it's not 0, and it's also in closed unit ball of A star, so this is in K. I want to say that so this K is non-empty. It's also convex. It's really easy to say that because P is linear map. And also P is convex. It's really easy to check it. And weakest are compact. One of the theorems, and when we work with extreme points, when we have a set which is convex and weakest are compact, it may reminds me the Krein-Milman theorem. Actually, I want to use this says that the extreme points should be non-empty. Why weakest are compact? It's of course very easy to see that. If you like, you can work with net if phi alpha in K, phi alpha goes to phi in ball of A star, we know that this is closed, and then phi of alpha f goes to phi of f is 1 because phi alpha in K, and so phi of 1 f is 1. This is element in B of A star, and phi of A is 1. So this is closed, and as a subset of B of A star, it's compact because B of A star is compact. K is closed, and then K is compact with weakest star. And this is also weakest star because K is a subset of B of A star. A part, even we can say like this is actually, according to the notation before, lambda inverse of f, lambda inverse of 1 intersection with B of A star. This is weakest star continuous, so with weakest star compact, and we, as a subset of B of A star, will be compact. So according to Krein-Milman theorem, extreme point of K is non-empty. By Krein-Milman theorem, extreme point of K is not empty. For example, let's be in extreme point of K. I want to show that this is actually extreme point of ball of A star, and so it would be like delta X in Choquet boundary. So if P is the average of Phi1, Phi2 over 2, and where Phi1 and Phi2 are in K, B of A star, then like here, exactly, like here, we can say that Phi1 and Phi2 also in K and use this extreme point of K and show that Phi is equal to Phi1 is equal to Phi2. Okay, then to be in K, it's enough to phi of F should be 1. Anyway, then phi of F is 1, Phi1 of Phi2 of F, sorry, F. But there are elements in the unit disk in C because absolute value of phi, for example, for phi at most norm of phi, 1 norm of F. This is 1, this is 1, so this is 1. And so 1 is the extreme point for the closed unit body in C. We can say that. And finally, Phi1, Phi2 in an extreme point of, in K. And so because phi in an extreme point of K, phi should be equal to Phi1 and Phi2. Then phi is an extreme point of ball of A star, and so phi is in the form of delta X for some, of course, this is unique in Choquet boundary. Then each F attains its maximal modulus at some point of Choquet boundary. As an example, of course, I want to leave it to exercise, but the Choquet boundary as X is the whole X. It's not hard at all. Just you have to use Riesz representation theorem and just prove it. Of course, I also obtained this example from the next theorem. But without this theorem, we can obtain it just by the definition of Choquet boundary. You have to show that if X in X, delta X is an extreme point of the dual space of C of A X star, and then just use Riesz representation theorem to make connection between functionals and measures, and just show that the delta X is an extreme point of voila, C of X star. But we can obtain it from the next theorem. after this definition, by Banach theorem, and of course, Rees representation theorem, for each P in T of A, of course, for each E A star, but we consider T of A because of definition of Choquet boundary. For it, there exists mu in M of X such that T of F is integral of F T mu on X for each F in A. And of course, norm of mu is the norm of phi, which is, we know that this is 1. And phi of 1 is 1. This is exactly mu of X. So mu is a positive measure. It means that for each Borel set, measure of this Borel set is non-zero, non-negative for each Borel measure, Borel set. They are of course probability measures. Mu is a positive measure. I mean that the range is just mu is a positive measure. The range is just from 0 to infinity. Of course, not infinity itself because it's a finite measure. Is a positive measure. I mean it, or this is actually probability measure. Such a positive measure for each phi is called a representative measure for phi. Such a measure mu is called a representing measure for phi. And using this representing measure, I can say a nice characterization of points in the Choquet boundary. I can say that X is a Choquet boundary, is element in a Choquet boundary if and only if the only representing measure for delta X is the Dirac measure or point mass measure at X. You know, Dirac measure or point mass measure, it means this is this measure delta, for example, epsilon X in this sense, I told you. I use epsilon X for Dirac measure at X. It means that A is 0, X is not in A, E is better because A for function algebra. And if X in A, E, we have 1. This is Dirac measure or point mass measure. Okay. let's A be a function algebra on X, then X is in Choquet boundary if and only if epsilon X is the unique representing measure for delta X. This is the point mass measure or Dirac measure, the point mass at X, or Dirac measure at X. For this part, assume that the only representing measure is Dirac measure. And I want to show that delta X is an extreme point of unit ball of A star. If delta X is like T, P1, P2, where P1, P2 in ball of A star, and T between 0 and 1, then from this representation theorem, we can say that from this representation theorem, there exists mu1, mu2 in M of X, norm of mu1 and mu2, both of them are 1. Instead of P of A star, let's say that P of A, because it doesn't matter, as I told you, it doesn't matter. It says that delta X is an extreme point of P of A star or T of A star. But if I say, for example, T of A star, I should say, first of all, I should say that, for example, from this equation, I have norm of phi1 and phi2 in 1 is 1. And so it takes time. And of course, phi1 of 1 is 1, phi2 of 1 is 1. So I prefer to just change it with T of A and nothing more changes. And this mu1 of X, mu2 of X, such that P and so according to this relation, f of X, rewrite it with this relation, the integral of f t mu1, 1 minus t, integral of f t mu2. And write it like here. F d t mu1 plus 1 minus t mu2 for each f in A. So it itself is a representative measure for delta x. C mu1 is a representing measure for delta x. But the only representative measure is Dirac measure. So T mu1 Dirac measure. And from this, we can obtain easily x is in a Choquet boundary. Because mu1 and mu2, both of them will be Dirac measure. And from this, for each E Borel set, which contains x, we have not here consider x is not in E, then this is 0 at E. They are non-negative, so they have to be 0. And also mu1 of x, mu2 of x, this is 1. And so their elements, mu1 of E is at most 1, mu2 of E at most 1. Is the 1 is the unit, the extreme point of unit ball in C, so we have 1. And from this, we can say that mu1, mu2 is, epsilon x, and corresponding functional here, phi1 and phi2 should be delta x. For the converse, suppose that x in Choquet boundary of A. I want to say that each representative measure is Dirac measure. And let mu be a representing measure for delta x. For each Borel set E with mu of E less than 1, greater than 0, we have delta x is mu of E L1 plus mu x minus E L2, where L1 is this functional. It's clear. It's 1 over mu of E, because finally we want to have f of x. Integral of f d mu on E, and L2 of f is 1 over mu of x minus e integral of f d mu x minus e. We don't have any problem here. But they are functionals in P of A star. X is an extreme point, and so L1 and L2 are equal to, okay, it would be better I raise another chalkboard anyway, that I want to use this. And since X in Choquet boundary of A, then L1 and L2 are equal to delta X. I need only L1, just so I write L1. Let's write if we have instead of that. Okay, 1 over mu integral of f d mu is f of x for each f in A. This is an important relation. I want to use it. Actually, I claim that each f is f of x almost everywhere. I mean that the set of points which f of x is not, f of t is not, for example, f of x, this set is a null set. Okay, we show that f is for each f in A, f is equal to f of x almost everywhere. Of course, mu are almost everywhere. Here just we have mu, and so it's clear mu. But mu is positive. So, for example, if f is u plus iv, integral of f, it means an integral of u plus integral of this, and this is real value, this is real value, and if it's, for example, u of x plus iv of x, it should be the same, equal to this one, and this one equal to this one. So we can say that, for example, I just consider real of f, and so it's enough to consider f is real value. And then v is, of course, v can be, this is, and so we have any problem with v, of course. And finally, we get f is f of x almost everywhere. So, it's enough to consider f is real value. Thinking about it. Suppose that f is not f of x almost everywhere. So for a contradiction, suppose that it's not true almost everywhere. So it means that the set of points f of t is not f of x. Measure of this set is positive. But you know that mu is a regular measure, and especially its inner regular. So, for example, mu of this set is supremum of mu of f when f is compact inside E. So we can say that there exists compact set such that f is, for example, less than f of x on f. The other side, of course, similarly obtained. F, before that, mu of f, of course, positive, and f is less than f of x on f, according to inner regularity of measure. Similarly, the case where f is bigger than f of x is obtained. So we consider just this one. Since f is compact, f is continuous, so we can consider maximum of f, which is strictly less than f of x, because f is continuous. There exists R such that f or in R, it doesn't matter. F is at most R, strictly less than f of x on f. And take the measure on f. Shows that integral of f on on f, it has most R. Integral here is mu of f. And this is f of x, mu of f. But this is contradiction by this formula. And so it shows that f is almost, oh, sorry, I forgot to show that mu is, just its contradiction to show that f is almost everywhere f of x, not for mu is just Dirac measure. It shows that f is f of x almost everywhere. And just it's enough to show that mu is the Dirac measure and support of mu is just x. It's not hard, of course. If y in x and y is not x, then we know that function algebra separate the points. F of x is not f of y. F is continuous, so we can find a neighborhood around y such that f of x is not f of all elements in that neighborhood. So from continuity, there exists V neighborhood of Y such that f of x is not equal to f of z for each z in V. But you know that f is almost everywhere f of x. So it means that from this point, it shows that mu of V is 0. And mu is outer measure. And then mu of Y cannot be in support of mu. The element, just element in support of measure is x, and then mu is just Dirac measure. Mu is positive, so mu is delta, sorry, epsilon x. Now it's finished. And for example, Choquet boundary of C of x is x. Choquet boundary of Cn is I, because the only representing measure is Dirac measure, and also here because Cn of I is dense in C of I. And actually Choquet boundary of A is the same as Choquet boundary of A with sup node. And of course Choquet boundary of Lip also is x. The next definition, just I have to say a little fast, just forgive me, because I need to cover some things. That's why. Let A be a function algebra on X, a point X in X is a S-string boundary point for A if for each neighborhood V of X, there exists F in A such that F of X is 1 and it's the superior norm of F, and the absolute value of F is less than 1 on X minus V. We can say that if A is function algebra and if X is a S-string boundary point for A, just let me write like here. to save time. Then X will be in Choquet boundary of A. Of course, the converse is not true, even for Banach function algebras. But for uniform algebra, it's true. It's a little technical, but you can find it in any books on just dealing with functional algebras. Okay. If X is X, then it's trivial, then it's clear because Choquet boundary is non-empty. So X would be element in Choquet boundary. And otherwise, take any proper open subset of X like V, because it's a strong boundary point, then exists F in F A such that F of X is 1 supreme norm of F, and absolute value of F is less than 1 on X minus 1. I want to show that each representative measure for delta X is a direct measure and use just the previous theorem. Take mu be a representative measure for delta X. So we have 1 is integral of f d mu, because it's f of x, delta x of f, and so we can say that because mu is positive, which is integral of 1 d mu, so integral of 1 minus real of f is 0. This is non-negative function, so it shows that 1 minus real of f is almost 0, almost everywhere 0. And so imaginary of f is also almost everywhere 0 because norm of f is 1. Anyway, f is 1 almost everywhere. Hence, f is 1 on support of mu. But outside V, the absolute value of V is less than 1, so support of mu should be a subset of V. So mu of V is 1. It works for each neighborhood opens subset of X containing X, and mu is autoregular, so mu of X should be 1. And this is a positive measure, so it's direct measure. And so by the previous theorem. Um, for example, um, it's easy to, for example, by horizontal lemma, you can say that each point in X is a strong boundary point. For Cn, it's easy to even define such a point. For a leap of X of sort is, for example, f of t, 1 minus d of t and x, 1 over d of t of x. This element, it's a suitable function, works for each neighborhood of d of x. It doesn't matter, it works for each neighborhood. And so each point again is an extreme boundary point. And I mean that this is another way to say that Choquet boundary of C of x and Cn and lib of x is the whole x. For Cn, of course, I. The first one by horizontal lemma, and for Lipschitz, this function works. Just I would like to mention one more definition, but maybe just leave the theorem without proof. But anyway, I would like to mention this concept. This is Choquet boundary. The intersection of all closed boundaries for a function algebra on X is called the Shiloh boundary. For A, and denoted by round of A, sometimes comma of A is also used for this case. Let A be a function algebra on X, then Choquet boundary of A is Shiloh boundary of A. Let's write here for simplicity. So it exists and it's minimal closed boundary. It's the smallest closed boundary because it's intersection of closed boundary. Let's say proof very, very fast. We know that Choquet boundary is a boundary. So Shiloh boundary, and the closure also is trivial. It's trivial that it's boundary. And Choquet boundary is the intersection of all closed boundaries. So it means that Choquet boundary is a subset of Choquet boundary. So this part is clear. For converse, I show that if we show that if E is a closed boundary for A, then Choquet boundary should be subset of E. And finally, we get the other inclusion. And for this purpose, define B as this subset of C of E, like the f of E, such that f has an extension to a function in A. Because it's in a boundary, so each function has just one unique extension. And so, because supreme norm of f on x with supreme norm of the restriction of f on E is equal, each f in B has a unique extension like ft in A. And B is a function algebra on E. Define function like this. Define T from B to A, which takes F to Ft. This is isometry because supreme norm of F and Ft are the same. And this is by isometry, I mean linear, surjective, maps which preserve their norm. I mean that linearity and surjectivity are also assumed. T is an isometry. It's really easy to check. Then TSR from AS adjoint of T, isometry. When we have isometry, because unit ball of ASR goes on to unit ball of ASR, it's easy to check that extreme point of ASR, ball of ASR coincides with the set of extreme points of ball of BSR. I use this method many times in isometries. Okay, here's sort of extreme point of ball of ASR is extreme point of ball of BSR. Okay. Then for each x in Choquet boundary of A, TSR of delta x is an Choquet boundary of is in extreme point of ball of BSR, and so there exists one y in Choquet boundary of B such that TSR of delta y is delta x is delta y. Then according to the definition of TSR, T of f of x is It means that, yes, okay. Yes, anyway. It's f tilde of x. And this is f of y, f in b. Sorry, I forgot to say, and alpha, of course, in t. Maybe we have some coefficients, but it's not important because it shows that absolute value of f tilde of x is, sorry, f. Especially for each g, for example, in A, g of x is g of y in absolute value. But I separate the points. Of course, I told you g of x is not the same of g of y, but it's really easy to check that with all, just with constant, you can see that with absolute value, they, of course, they separate the points. And so this is in E. And Choquet boundary of x should be in E. Then Choquet boundary of A is subset of E, and its closure, of course, is subset of E, and this completes the proof because it works for each, let's say, more thing, and then here's this. One nice and of course, Shiloh boundary of these algebras is the whole underlying space. And for another example, Choquet boundary of disk algebra and Shiloh boundary of disk algebra is just C. Of course, because the principle of maximal modules, each function here attains a maximal module as in some points of t. So t is a closed boundary, and so it contains this. And for each lambda 0 in t, the function like here, it shows that each t should be in Choquet boundary of AD. And if you combine this relation, you can obtain that Choquet boundary of AD is Shiloh boundary is T. This bar here is, sorry, I wrote it by mistake here. It's T. And here, this is, of course, that's why you can follow better this part. And let me write it here. I think it's more suitable. Now, a nice theorem concerning isometries between uniform algebras. And then I want to obtain the celebrated Banach-Stone theorem. Really nice. Okay. Let's the uniform algebras on compact Hausdorff space of X and Y respectively if T from A to B is a surjective linear isometry, in short isometry, then there exists a homeomorphism like P, like H from Choquet boundary of P onto Choquet boundary of A, homeomorphism. T f of y is T1 of y, f of h of y for each f in y in Choquet boundary of B, and let's write it here because save the space. T1 is 1 on Choquet boundary of B, and this one. True. And since C from A to B is an isometry, like the previous method, then P star from B star onto A star is an isometry. And so exactly if extreme point of ball of A star is T star of extreme point of ball of B star. Then for each y in Choquet boundary of B, T star of delta y is an extreme point of ball of A star. And so according to know that these elements, there exists alpha may be related to y in T, and X may be dependent on y, such that in Choquet boundary of A, such that T star of delta y is alpha y delta xy. But I want to show that this is exactly unique. Anyway, so for each f, Tf of y is alpha y, f of x, y. If we put, sorry, that's right here. If we put f1, so we get alpha y is T1 at y. And then Tf of y is T1 of y, f of x, y. I say that this element is unique because if, for example, Tf of y is alpha prime y, f of x prime, then using this relation, we can say that f of x prime y is equal to f of, for each f of x for each f, but A separate the points x prime y is xy. So this argument permits us to define a map H by the above argument. We define H from Choquet boundary of B to Choquet boundary of A such that H of y is exactly xy. Then we can rewrite this formula like this. Tf of y is H of y, f of phi of y. H is continuous because if y alpha goes to y, then for each f, Tf is continuous, Tf of y alpha goes to Tf of y. Sorry, I made a mistake here. Oh man, C1, sorry. So when you have, when you're in a hurry, then maybe it happens. And so from this relation, we can say that f of each y alpha goes to f of hy. And yesterday I told you topology on X coincides with A topology. That's why it's because it's for each F. H of Y alpha goes to H of Y. So H is continuous. And similarly, we can have this discussion for T inverse, and we can find function like H for T inverse. Similarly, there exists continuous function like K from Choquet boundary of A to Choquet boundary of B, continuous, such that T minus of G at X and it's easy to see that from, for example, T just I want to which one? It's exactly T1. It's really easy to check. I want to write it just a little faster. This one is 1 in B. So this is for T1 minus, yes. Just I put here, for example, I use for T1 this part, T1 of X, T1 of K of X. And for this part, I use this one, T1 of Y, T minus 1 of 1 at point H of Y, nothing more. X in Choquet boundary and Y in Choquet boundary of B. And from this, easy to see that F can be write like P minus C of F at X. And using this relation, you can say that this is exactly, if we continue, it's really easy, just using these two relations. And we finally get, this is F of H of K of X. And for example, for G, K of T minus 1 of G at Y. This is G of K of H of Y. Okay. For each F, we have F of X equals to this one, G of Y equals to this one. But A and B separate the points. Finally, we get H O K is identity, K which is identity. So H is inverse of K and K is inverse of H. And so H is homomorphism. H. Because the only thing I need to show here is homomorphism, and using T inverse, we can have it. And let me say the famous theorem by Banach and Hosseini. Using this fact, Choquet boundary of C of X is the whole X. If C from C of X onto C of Y is an isometry, then there exists phi from Choquet boundary of C of Y to Choquet boundary of X, phi, like H, because I use H, homeomorphism, such that absolute value of T of 1 is 1 on Y, and T of F is T of 1 FO phi on whole Y. This is a nice Banach-Hosseini theorem. Okay. Of course, just let me add, and it's not, from this theorem, you can obtain nice theorem by Rudin, Vermeer, Diulu, and I just leave it as an exercise, but I like to mention here, it's not difficult to check it. You can, because you have the representation. If A and B are uniform algebras. Okay. If C is an isometry, then there exists algebra isomorphism and W in B such that the absolute value is 1, W is A inverse, and P of F is W P of F. That's it. Actually, phi of F should be W inverse T of F. We should define like this. Anyway, many thanks for coming. I hope this course will be useful for you and enjoy this course. Thanks and bye. I hope you have a good day today.